Okay. Well, as we have some more individuals joining today, please take your time, answer the poll question up on the screen. It just gives us some data to be able to look at during the event as well as after. On behalf of the entire team at Environment and Energy Leader, I welcome you to today's webinar sponsored by Enel, Prediction to Reality, Demystifying Energy Storage Optimization. Again, if you just joined, there is a poll question up on your screen. Please take about 30 seconds to answer that. We will have time during today's event for questions from our attendees. During today's event, please submit all questions using the Q&A widget at the bottom of your screen. You will notice that there is also a chat widget. You can communicate with a member of the team. Please let us know where you are joining from, why you decided to jump on with us today, and what you hope to get out of the webinar. If you are watching this on demand, you still have the ability to submit questions because all questions that come in post-live event will be forwarded to today's presenters. And I just want to thank you for spending part of your day with us. We truly have a global audience on with us, so I know it is very late for some individuals and very early for others. So thank you for taking time out of your day to be with us. This event will be available on demand to review again. All you have to do is click the link that you used today or the link that's in your calendar, and you will be able to access the event once it has been archived by Zoom. At this point, I'm gonna turn the presentation over to Liam, and I will rejoin everyone for the Q&A. Again, thank you for being here.
All right, thank you, Jessica. Welcome, everybody. So the title of today's presentation is From Prediction to Reality, Demystifying Energy Storage Optimization and What Matters to Achieve Project Success. So quick introductions. My name is Liam Weaver. I direct our solutions engineering team here at Enel North America, and I'm fortunate to be joined by my brilliant colleague, Ryan Mann, who is a lead technical analyst on my team. And though it may not seem so from our vibrant and youthful faces on the pictures here, between the two of us, we actually have quite a bit of extensive experience through consulting, government, startups, education, etc., all within the clean energy and transportation electrification sector. So we've both been with Enel for over 5 years, and my team, including Ryan, focuses the majority of our time on evaluating customer opportunities for distributed energy resources, including solar, energy storage, and electric vehicle charging. And we do lots of technical modeling to size and predict what our systems will be able to do. We work with customers to ensure projects are feasible, meet their goals, and then hand it off to project execution teams to successfully construct and operate. So just a quick background before we get into the meat of the presentation today on where we're from. So we work for Enel North America, one of the largest clean energy developers in North America. Just surpassed a really incredible milestone of 10 gigawatts of installed renewables capacity across North America, just shy of 5 gigawatts of demand response. And then the focus of Ryan and myself's and this presentation's work is our behind the meter distributed energy resources business line, for which we have over 140 projects under management, as well as 15 plus years of experience, which in this line of technology makes us quite veterans. So one last point to highlight here is we're also a financier and operator of these projects, meaning that this is something that we support not only the operations of, but additionally, the funding and design and sort of turnkey solutions. So what are we going to talk about today? Narrowing down the scope to those behind the meter projects, really specifically energy storage, we wanted to review, in the past 15 years, what have we learned? What are some really critical components to help make projects successful, as well as the demystifying portion is focusing a good amount of our time on the mathematical part of it, including optimization and forecasting, as those can be sort of a danger of being, sort of buzzwords that, may not be entirely clear. So we're hoping to dig into that today, make it a little bit more clear. So I'll start off the presentation with a little bit of context on energy flexibility, why energy storage has seen such a big boom in recent years, spend time on those foundational concepts with Ryan on optimization and forecasting, and then close out with a little bit of some other factors beyond that that we found have been important for project success. So what is energy flexibility? Why are we here? I was joking, with Ryan and our team before the presentation that it wouldn't be a complete presentation without starting with a graph that goes up and to the right. But here I wanted to highlight 4 points, two on this graph here to the left, which are really in the first time in the past 20 years, we're starting to see energy demands across the nation grow once again. So this sort of stagnation period was driven primarily by a lot of energy efficiency improvements, which was really um, a great implementation of that technology. But as we look at kind of a peak of that, as well as just more people, greater demand, more electrification, more HVAC, more air conditioning, data centers, electric vehicles, we're now seeing demand grow yet again and quite significantly. And so that last point I mentioned is basically observation two, which is that the type of demand is changing. So the times that we use energy, the extremity of demand spikes, the shape of that demand is evolving and changing our grid. So if we look at graph two, we can see, after covering demand side, we see the supply side is changing as well. So the sources of electricity are changing as we move to a cleaner grid. The disparity of costs between middle of the day when the sun is shining or a windy afternoon and perhaps the middle of the night or a calm still morning when renewable resources are not generating, the differences between those times and the cost of that energy is dramatically different. So this graph is essentially just showing the rise of new sources of electricity, specifically from renewables in the recent years. So that brings us to point four, which is that these phenomenons are forcing utilities to adapt their policies and pricing structures to find new ways to incentivize behaviors to match and balance demand and supply on the grid. So to understand how these trends are affecting individual businesses, we need to break down how those utilities are charging their customers for this electricity. And so here's a simplified structure of some of the different ways a utility may charge for the electricity of, let's say, a commercial or industrial scale business. So some of you may be familiar with these concepts, so I'll keep this brief. But these are foundational concepts for the optimization problem that Ryan's going to set up here momentarily. So first component is probably the easiest and simplest to understand, and this is energy charges. So how much energy do you use? You're going to be charged for that amount of energy. The sort of nuance here is that there are now an increasing amount of time of use applications to these charges, meaning certain times a day may be more or less expensive to use that energy, as well as we're seeing a rise in more dynamic energy rates and rates that may be based on real-time pricing out in the market. So these rates are evolving, but again, this general component is the amount of energy that's used and the time in which it is used. The second component here is demand charges. So this is not based on the quantity of energy, but the single highest peak of demand within a given period of time. So these are often monthly, although they can be daily or other periods of time as well. But this represents essentially the cost of the utility delivering that large amount of power instantaneously to your site. So you can imagine that the distribution facility needs to be sized to provide peak power to that facility at the highest demand during a period of time. That kind of leads into a bit more extreme inversion of this, which is coincident peak charges. So again, different utilities may or may not include this portion in their tariffs, but those that do charge for across the entirety of their grid, what is the highest peak period, and how does that translate specifically to an individual customer's usage during that period? So you can imagine that there may be 10, 5, even one single event per year that a utility has to design for to meet a massive amount of demand and a massive amount of electrical infrastructure to support delivering that demand to their customers. So this huge strain across the grid can mean potentially even a single gas-powered plant that's online for only a few hours per year, simply to accommodate for that, let's say, hottest summer day or a period in which there is a huge amount of demand. And so this is quite expensive. And so you can imagine that these charges, even for short periods of time, can be pretty significant. And lastly, grid services is another form which is almost the reverse of this, where rather than the utility charging you, they actually provide incentives for businesses to reduce demand or provide other services to the grid during certain periods. And so there may be notification times that vary, which we can talk through a little bit later. But these are essentially opportunities for businesses to help the utility manage those periods of strain and generate revenue. So final point here is, these are all ways in which energy flexibility can be leveraged in order to reduce a lot of these costs and enable businesses to, rather than spend, a huge amount of their expenditure on energy and electricity, on other things, things that actually make their businesses better, things that improve their products, their services. And so that is what we want to talk about how to do today. So that's enough for me for now. So I'm going to take it over to Ryan to translate this concept into an optimization problem. Over to you, Ryan.
All right, thanks, Liam. Let's see, so in this next section, Optimization Matters, we're going to cover some of the details about how NL optimizes the value that on-site resources, with sort of a particular focus on on-site energy storage, oftentimes paired with solar, can deliver to the host customer where this resource is located. So we're talking about behind the meter batteries here. So if we take the electricity costs that Liam talked about in the last slide, and we formulate them as what's called a mathematical optimization problem, minimizing those costs or minimizing that net electricity spend means creating what's called a cost function that includes all of the individual line items that Liam talked through, all the line items that are on the customer's bill, as well as those grid services revenues that offer the opportunity to offset or net against some of those positive charges. And so those grid services revenues can include typically demand response, demand side management, program capacity, and energy payments. And NL has a long time focus on grid services and on sort of fully integrated co-optimization between reducing the customer bill and capturing revenue from these various grid services programs. Because it's important to note that participating in those programs can oftentimes mean a slight reduction in the bill savings that an energy storage system can provide, but more total value overall. So there is some degree of trade-off or tension oftentimes between reducing the customer's bill with an energy storage system and delivering grid services revenue. But participating is, if properly selecting programs to participate in, it should always be a net positive. And in addition to minimizing those costs, there are a number of constraints that need to be met. And this is, for this slide, just showing the absolute most essential core constraints here. And so this includes respecting limits on the battery's state of charge, having to stay between 0% and 100%, as well as upper and lower bounds on charging and discharging of the battery. And of course, there are many others, but we will get to those in future slides, because many of those are market specific or even project specific. And yeah, sort of as alluded to, that formulation on the prior slide is sort of deceptively simple because the optimization software that is controlling the dispatch of the energy storage resource is trading off between multiple competing value streams. And so, for instance, as Leah mentioned, many commercial industrial sites have demand charges, but multiple demand charges. Oftentimes there's both a 24/7 or non-coincident facility demand charge that can be managed by just simply flattening the customer's overall load, as shown in the graph here. But there can also be time of use demand charges that involve effectively taking a chunk out of energy usage and flattening it during specific hours of the day. And in addition, as Leah mentioned, the energy charges are also time varying in many cases now, including, and increasingly dynamic. And that also, typically can align with when the high demand periods can happen for a particular customer, but depending on load profile, those two economic objectives can be in tension with one another. Next, as mentioned, there are these grid services opportunities, some of which take the form of the coincident peak charges, which typically appear on the bill and are a positive charge, but also demand response programs, which are payment for reduction in load rather than charging for your consumption. And those typically, the compensation for those typically happens outside of the customer bill. But both of them involve reduction during, they are event-based net load reduction economic incentives, with some additional nuances between the two, including the fact that typically for coincident peak programs, the customer does not know when the peak hours are until the very end of the year, and that is where NL's forecasting capability can come in to predict those events and dispatch the battery intelligently during the hours that are most likely to be the coincident peak hours. And then finally, if we're talking about solar plus storage and sites that are capable and allowed to export to the grid, increasingly what we're seeing is export compensation rates that are decoupled from the retail rate. So there's something different from the, say, time of use retail import rate. And this is an additional challenge and complexity to manage, but also can create new opportunities where now, instead of simply arbitraging between the different retail rate values, say in a time of use scheme, there's now the opportunity to effectively arbitrage between the export compensation rate and the import or retail rate. And so, increasingly this looks like not just doing sort of simple self-consumption, as many residential solar customers are familiar with, but a sort of smart self-consumption where in certain hours and certain months of the year, the goal is to avoid exports because they're not compensated very much. But increasingly in some markets, there can be cases where the export compensation rate is actually greater than the retail rate. And that is where the energy storage system can play a role in exporting and helping out the grid during those hours. And sort of continuing on this theme, there can be a lot of market-specific or project-specific additional cost function components, as well as constraints that make this problem more complex for sort of real-world solar and storage projects. So in addition to everything mentioned previously on the sort of cost or objective side of things, many customers are interested in meeting sustainability goals in addition to minimizing their electricity spent, and that this can, there can be regulatory reasons why, for instance, an energy storage system might be required to sort of maximize its beneficial greenhouse gas impact, as well as voluntary sustainability reporting reasons. And there are certainly a few different potential ways to do that. There are different sort of lenses or frameworks for thinking about shifting load and minimizing scope 2 emissions. And in addition, it's worth noting that some customers with behind the meter storage are interested in backup and resilience. And so that can be an additional sort of objective for the battery that, in some ways can be in tension with goals like reducing the customer bill. And then on the constraints side, in addition to the ones that were previously mentioned, oftentimes there are utility set rules around import and export of the site, as well as import or export, export limitations specifically for the energy storage system. So there are some markets and some projects where the site as a whole, including the solar, are allowed to export to the grid, but the battery storage system is not. And NL's energy management system, all of the kind of core mathematical optimization work is informed by all of these data streams that are sort of flowing into our software. And this includes the site level data on demand and on-site generation. It can include weather data from the cloud, as it were, and that's informing demand forecasts and generation forecasts, as well as things like predicting peaks. We have utility tariff and rate data that are sometimes static, sometimes dynamic, but a really core input. And then grid services program parameters that are used to inform when are the programs going to happen, which days and which hours. And using all of that data, that is where our optimization software is figuring out how to dispatch the battery in order to shape the customer's load and deliver the most economic value. And we are, letting the software do the short-term decision making, but we also have the ability to monitor the asset's performance, see if everything is going all right from a software, hardware, communications point of view, and intervene if need be, particularly as it relates to things like hardware failure, calling in operations and maintenance people. And so now that sort of concludes the mathematical optimization side, sort of the dispatch of the battery. But that dispatch is informed by our forecasting capabilities, which involves a sort of interrelated but separate sort of set of software and set of mathematical techniques. And so there are a number of different, sort of as alluded to on the prior slide, there are a number of data streams coming in, and many of those are used for forecasting purposes. So this includes predicting the on-site load, and it's worth noting that predicting load for an individual customer, especially a commercial or industrial customer, is quite a bit more challenging than something like forecasting system level demand, where the load of many individual customers tend to kind of cancel each other out, but a single customer can have quite a bit of randomness to it. And similarly, PV production or other on-site generation can be somewhat challenging to forecast, even with good quality weather data for the site. So definitely net load is an important variable to predict, especially as it relates to markets with demand charge management as a primary value stream. But on the grid services side, we are predicting things like system peaks for coincident peak reduction, figuring out which days and which hours are most likely to be the peak hours, and then dispatching the battery so that in case that hour does turn out to be the peak hour, we have reduced the load and reduced the customer's bill. And to give it sort of a sense of what this looks like, typically for a given data stream, say customer demand, there are a number of different predictor variables or feature variables that can be used to predict future values of that data stream. So that can include things like time of day, day of week, weather variables like temperature or humidity, as well as so-called autoregressive features where we're using current or recent load as predictors of future load. And the idea here is that we take our historical data, we train a statistical model or a machine learning model using that historical data, we make predictions using that, and then over time we can update and retrain the model using new data as it comes in. And the idea is that that can make our predictions more accurate, as well as capturing changes in, say, the customer load that can happen over time. So the relationship between all of these input variables and our target variable thing we're predicting evolves over time. And the advantage of using a sort of data-driven model is that it can evolve along with it. And yeah, and in addition, different customer types, different end uses, each have different electricity consumption profiles. And so there's value in customizing the forecast model type and fine-tuning it to match with those customers. So in addition to selecting feature variables that are relevant for a given customer, we can also pick different model types, as well as different so-called hyperparameter values that are sort of knobs that we can turn in order to sort of better fit a given customer. And I would say maybe the most relevant thing to sort of call out is that commercial buildings, say an office building that tends to have a fairly predictable load profile, may require quite different forecasting techniques from a heavy industrial customer that has a highly unpredictable load profile. And so we can customize different forecast types to different customers in order to deliver the best storage dispatch performance. So to give a specific example here, this is one of our real world sites. And yeah, it's worth emphasizing that this is a very, very difficult site that has a spiky industrial load and two distinct solar arrays that were installed at different points in time, as well as a set of behind the meter wind turbines, which are a rarely, fairly rare occurrence. And these sample numbers that we have on the right here are indicating the value of high quality forecasting and optimization, both for in the field operations as well as when simulating a prospective project opportunity. And so just simply simulating the site using historical, actual, say, load and on-site generation data, and then applying some sort of fixed industry average derate factor would, for this site, lead to over-promising results for a customer like this that has such a challenging, unpredictable load profile. But on the other hand, using a less sophisticated, not very customized set of forecast inputs would lead to really low economic performance for this site. And so if we combine sophisticated software, customized forecasting, and subject matter expertise, such as our asset management team that's keeping a careful eye on the site and looking for, continually looking for how we can deliver more value. That is how we can deliver high real world performance that closely matches what we had predicted in our upfront modeling. And so on the sort of upfront modeling side, which is really the core focus for Liam's team, NL worked with BNV a few years ago to have our pre-sales modeling evaluated by them, doing a series of interviews and sharing with them a bit more detail about the methodology that we use. And they determined that our modeling capabilities were made us industry leaders. And I guess it's worth noting sort of the particular challenge that we face on the pre-sales modeling side, because it needs to simultaneously be sophisticated enough to accurately represent those sort of future real world conditions when we are sort of operating the site. But it also needs to be flexible enough to handle new value streams and new markets. This energy storage space is evolving very rapidly, and the use cases for it are changing. And so we need to continually sort of be a bit ahead with our pre-sales modeling software, so as to kind of capture what these prospective sites might look like. And then on the real-time operations software side, we've invested a lot of effort in creating a hybrid cloud plus local software architecture that is really robust. And the idea is to allow for autonomous local operation in the event of some sort of communications interruption, which does happen even when you have multiple redundant forms of communication, but then still be able to pull global data about grid conditions or weather conditions from the cloud as they are made available. So having multiple sort of fallbacks and redundancies to handle things like communications outage. However, it's worth noting that delivering high performance in the field isn't just about having sophisticated software for making those dispatch decisions, but is about, without giving too much away from Leon's section as I pass things back, it's also about the people who are monitoring these sites and are working to deliver high performance, both in sort of short term as well as kind of long term optimization of these sites.
All right, thank you, Ryan. So yeah, super interesting stuff. I think time to close out with some final comments on beyond the math. So some of the other factors we found that matter, kind of alluding back to the original theme of after 15 years of operations, what are some key factors that help us to make these projects successful? And so we've seen performance is only as good as the optimization. Optimization is only as good as the forecasting. And the forecasting is only as good as the people, systems, and process that surround it. So I will just confess that it took me an embarrassingly number of times to try to spell the word iceberg in creating this slide. But I think we're all familiar with the term tip of the iceberg, and that today we've talked through optimization, machine learning forecasting, extremely critical components to how these systems operate. But what we haven't really dug into is all of these other factors that pop up when you're actually trying to build and maintain physical projects. So just a few of these bullets here, including tying back into the hardware side. So talking about APIs, data sharing, system architecture, and controls, not to mention the actual development, engineering, design, construction, procurement, commissioning, and O&M of these systems, as well as just in terms of asset performance monitoring and management, having people physically there, understanding which programs are still applicable, understanding the parameters of those, translating them back into the field, staying in tune with energy markets, new policies, new programs, new tariffs, regulatory compliance. We talked about some different programs that may require greenhouse gas reductions, or other, utility requirements, as well as a network operations center. So how are we getting real-time responses from these systems as to how they're operating, and who is sort of reading those signals and alarms and responding to them? Can we troubleshoot remotely if there's an issue with the system? Do we need to send people out, etc.? So as we put on our scuba outfits and dive into the ocean, this is a bit more visualization of the hardware side of the picture. So this is essentially what we've been talking about today in physical form. So you see the orange highlighted parts here are where a lot of the optimization and forecasting happens, both within the cloud as well as within the physical site controller on site. But you can see here all the other surrounding electrical infrastructure, including not only the distributed resources themselves, like solar, wind, or EV charging, but also just the electrical components, talking about AC load panels, power converters, meters, grid infrastructure, battery cells, energy management systems, switches, etc. As well as you can see in the upper left-hand corner, what the system physically looks like. So, you can imagine there's quite a few safety protocols and procedures, permitting, interconnecting to ensure that these storage systems, transformers, switchboards are all interconnected safely and successfully so that they can actually operate and achieve those savings that the optimization and forecasting enable. So when we look back out on the asset management and energy market side of things, you can imagine that each utility, each co-op, each independent system operator, each region has its own rules, its own methods, its own tariffs, its own dynamic, non-dynamic rates, direct access programs, incentives, coincident peaks, etc., which all need to be understood, successfully managed by a registered asset manager who has that market access, maybe even helped create the program in the first place. And so across all of these regions, again, these programs may have different event times, different parameters, different notification signals. And so it's imperative to have a team that's managing and understanding what's going on across the nation. So this is an example from our team, but the point here is really that if you're implementing an energy storage project or a distributed energy resource project, you need the right team of experts. So it's not all just about the AI, the optimization, the forecasting, but it's about the people behind that. So here's just kind of an example model of some of the team members that we find, really help on a project specific basis. So starting on the far left, people who can communicate with, advocate for, understand, and relay specific client needs back to the business. The solutions engineers, including yours truly, who model and translate those needs into a technical solution that's feasible and can be successful. The development engineers who take that solution design and actually develop and apply for interconnection, permitting, etc. The onboarding and construction management teams who take that design and go out and build the project, commission it. The asset management team, which we've talked about a little bit, who accounts for the performance of the system. And then the operations and maintenance team, who's going to be there in the next 20, 25 years of these projects' operations, ensuring that it's still operating and we have preventative and corrective maintenance support. So in addition to that project-specific team, the little dark green box on the right highlights some other teams that may be working behind the scenes as well. So you're going to want a dedicated team for safety and environment, energy markets, policy and regulatory advocates, as well as a dedicated hardware testing lab to ensure device compatibility, testing for maintenance. We found this to be critical. Ours happens to be up in beautiful Spokane, Washington. But you don't want to go out on site after assigning and building a project only to find issues in hardware controls or compatibility or things that could have been solved prior to implementation at a testing lab. Additionally, just a couple other teams, the advanced simulation dispatch controls teams, and many more. So you can imagine that all these algorithms and forecasting methodologies are again developed by a team of people, computational scientists, development engineers, et cetera, who are improving the code base to make this all possible. So we want to conclude today with just a picture of a kind of a real world project and what does all of this work actually enable in the field. So, we only really had time to spotlight one of the 140 projects we shared at the beginning of the presentation. But we chose one that just had its ribbon cutting very recently, a couple weeks ago, down in Puerto Rico. So this is a very exciting project and a fantastic application of the concepts that we've talked about today. So not just the theory, but pulling this into reality. So this is Puerto Rico's largest clean energy microgrid in history, built by a lot of the teams you saw on the previous slide, alongside our client partner Eaton, and fully financed by now. So this is a system where the optimization, the forecasting is all in play. When the system's connected to the grid, generating a lot of those different forms of savings that Ryan talked through in the optimization section, as well as with additional constraint that we didn't spend much time on, but we touched on briefly, which is the ability to reserve a portion of the battery for certain events for resiliency. So this project was actually inspired by the hurricane back in 2017 and all the power outages that continue to happen across the grid in Puerto Rico. And so the system actually has the ability to not only generate savings while it's connected to the larger grid, but disconnect from the grid in the event of an outage and continue operating and generating power on site. And so, again, we don't have time to dig into that in full detail, but we did actually do a previous webinar on resiliency and have an ebook on that as well that we'll be able to share. And I think I don't know if we mentioned this at the beginning, but we will be sharing a follow-up email with all the slides and an ebook related to this topic that we discussed today to all the registrants. So feel free to look out for that. But just closing out on this project again, just to emphasize that these types of solutions for energy flexibility actually don't have any impact on the operations on site. So these are all operating in the background, behind the scenes, generating those savings, and it's not something that somebody at the plant needs to be there to turn a switch on or off, or needs to provide input into how they're using energy. The point of all of this is that it's able to operate independently and achieve the objectives behind the scenes. So in conclusion, the grid is changing, the world is changing, our relationship with electricity is changing. And so to embrace that change, sort of lean into it and seize the opportunity, we can leverage technology like energy storage and distributed energy resources, mathematical concepts like optimization and forecasting, and real people with real experience, systems, and processes to save money, but also really enable a cleaner and more sustainable grid and allow individual businesses to focus more of their time and resources on the things that matter to them and not on paying their electricity bills. Like we discussed at the beginning, things that can help improve their products and services, all the while making the grid a little bit cleaner and more efficient. So I'm going to pause there. Hopefully, there's been a little bit of demystification during today's webinar. If not, I believe we're going to transition over to a Q&A portion. So please type your questions in the Q&A box. I think Jessica will be helping us out monitoring some of that. But thank you all again for tuning in, and we'll go over to questions.
Fantastic. And thank you for all of the information that you provided, especially this last slide. I think it's very applicable and it's something that the attendees will take away from them. So my question first to Liam, I know you just finished talking, but if you could tell us the top 3 questions that you get when working with a new client on their energy storage optimization goals?
Yeah, I think top 3 questions would be, one is related to operations maintenance. So that's always a critical component is, okay, these are 20-year-long systems. How do we, ensure that they're continued to be around for the long run? 2, I would say is how do we kind of relate it to what we talked about today, which is why we designed a presentation around it, which is how do we actually predict and ensure that we'll be able to deliver the savings that we project. And third would be, I think, really just, more project specific as to how does this, how does my utility charge me? How does this reduce this cost? What can I be working with locally? How can I apply these broad concepts to my specific project? So those are the questions. Do you want me to do the answers as well?
Why not? Yeah.
Okay.
Unless Ryan, did you have anything you wanted to add before Liam
Yeah,
jumps into
Ryan,
those
any other
answers?
questions we get frequently?
No, I think I'll let Liam answer his own questions.
Great. So remind me what I said. So the first one was around operations and maintenance. So we covered that a little bit. Let's see if I pull that slide back up. But yeah, I mean, that's why I think it's really important to either find a partner who can finance a project for you, or have some sort of agreement over the full 20-25 plus year of the term that ensures that you're going to get that ongoing support. Because there's a lot of focus and attention on the first year or two of building, construction, setting things up. But at the end of the day, the next 20 years are just as important as those first 2 years. And so that's kind of how we developed our financing program is, we are going to own the project. And so it's in our best interest, as well as our clients, to operate successfully, ensure that there's people ready to go if we need to replace any equipment, adjust any parameters, all that sort of stuff. So I would say finding some kind of financing partner with a long track record of success is kind of the importance of O&M. Second point was around prediction and achieving those savings. So Ryan kind of touched on that a little bit. Let's see, pull that slide back up. So this one, I think, is where it's really critical to take a close eye and ask lots of questions about, predictions you may be seeing in these systems, as the theoretical maximum performance is often not necessarily what you want to base your business case on. And so that's why we try to do as early as possible that forecasting screen in order to determine, hey, whoa, this site has 2 different solar systems. It's got wind. The actual demand is unpredictable. We really need to account for that before we actually go out and, project savings and operate the system. So 2 ways to do that is, one, just making sure expectations are right on the front end, as well as some of the stuff that Ryan mentioned around fine tuning those forecasts, being familiar with the programs on the back end to actually meet what is predicted. And the third question is really hard to answer because it's so specific. I think each customer has unique goals. And so that's why, we try to work, that's why we have this team that's kind of understanding how to translate those goals. These aren't sort of off the shelf products you can just buy and, place on your site. They're all fairly custom. And so each one kind of needs to be worked out in the kind of planning phases.
Thank you. Ryan, did you have anything you wanted to add? And I know we do have a follow-up question that came into the Q&A chat on that slide as well, Liam. On slide 17, sorry.
Yeah, I don't think I had too much to add. And I guess, yeah, for that second question on slide 17, it was about standalone storage versus solar plus storage, or in this case, solar plus wind plus storage. And I mean, the concept is very similar. I mean, I think when you have on-site generation, that is an additional data stream to forecast that, is an additional source of uncertainty as far as sort of the net load is concerned. But the concept is very similar, and it's pretty site specific, where there are some sites that are reasonably straightforward to accurately forecast, and others that are more challenging. And so, I think sort of the sweet spot for us would be a site that has, as far as demand track management is concerned, would be spiky but predictable, but you don't tend to see a whole lot of those. The ones that are spiky tend to also be somewhat challenging to predict, but we've spent a lot of time trying to develop software that is capable of predicting those as accurate as possible, but then also making dispatch decisions that perform well, even in the sort of face of that uncertainty.
Excellent. And I know just from a residential perspective, we have solar on our home. And before we signed on, we had the prediction of how much we were going to produce and whether or not it was going to cover. So it's even as a consumer, while we don't have it for our business, we have it for our home, that it's really important to be upfront, as you stated, as Liam stated too, and set realistic expectations and goals from the beginning. Because you can always, go above and beyond, but you want to be realistic from the beginning with the clients. So thank you for that. This is an interesting question, and it is one that we get frequently in webinars when we talk about different projects. So what was the most challenging project that either of you have worked on, and why, and what made it so difficult?
Great question. I'm racking through my brain of what project was not challenging. So yeah, I think each project has its own sets of challenges. This particular case study we pulled out because of the challenges on the forecasting side, but there's some other projects that come to mind where the challenges were more on the hardware and interconnection side. So particularly a lot of our larger projects in Ontario, we're looking at 20, 40, even 60 megawatt projects now and in behind the meter. And so you can imagine that those involve a lot of different stakeholders, permitting, utilities, interconnection to all be on the same page, as well as a design that is not impacting the facility operations. Maybe they have one site shutdown planned every 3 years, and we need to align our COD date with that time to commission the project. So as these projects expand in size, they also expand in complexity. And so, yeah, I would say that's kind of my short answer to the question. Ryan, do you have any other insights?
No, I think, yeah, as you said, it's very site specific. There's a lot of different dimensions to what makes a project challenging.
I'm sure. And then just to kind of piggyback on that, with the changing regulations, federal regulations, how does NL deal with, making sure that you are in line with the regulations as they, come out with new ones every year?
Yeah, so that's part of the sort of point here is having that business development regulatory team to really be in tune with that. We have regular sometimes weekly, sometimes monthly check-ins with each kind of regional expert, because as you said, these things are often evolving in real time and policies change, and so you kind of need at least dedicated people to be focusing on that. But I think the positive spin on this is that things tend to seemingly be always changing for the better. I would put in quotes, better for distributed energy resources, because more and more utilities and regions across the nation are seeing the advantage of deploying this technology and are creating new programs to incentivize it. And so really it's just a matter of keeping up with the good stuff and where we should be focusing our attention on next.
Yeah, and I guess one thing to add to that is that energy storage is it's a flexible asset in the sense that the value that it's providing in year one of operation could look very different from what it's providing in year 10 or 20. And yeah, unlike, for instance, something like solar, where, there is definitely more of a risk of sort of value deflation over time, whether it's utility scale or distributed, where, um, most likely the economic incentives are likely to move towards being less favorable sort of in the longer run. And with energy storage, it's capable of adapting more, as as these sort of economic incentives change. And as Liam said, in general, the trajectory is towards more, more favorable sort of advantage, yeah, more sort of more value streams to take advantage of.
Thank you for that. And I know we are almost at the top of the hour, so we probably have time for one more question. If you do have questions, further questions, please keep submitting them. And then you will also have the chance to submit in the survey that pops up at the end of this webinar. So how does the DER operating systems consider GHG versus cost reductions considerations? I've seen those priorities conflict, and I am curious how DER OS can be set or adjusted to focus on, for example, a GHG target while still considering a savings initiative. That was a mouthful. I know.
Let's see. So yeah, it's on one of these slides in the middle here. I think, Liam, it's the following one. But yeah, I think probably the simplest answer is that you can put an internal price on carbon. So if you have, say, kilograms per kilowatt hour, and you multiply that by dollars per kilogram, then now you're in dollar per kilowatt hour territory, and you can more or less treat that as an overlay to something like the retail rate.
Yep. And so, yeah, the point in the question is a fair one, that sometimes these can conflict, although we do see about, I would say, 90% of the time them actually being aligned, because if the utilities designed their rates and programs well enough, then those lower cost, more renewable energy periods are also going to be the less expensive periods. But for those kind of edge cases where maybe the facility load is not present during those periods or otherwise, it really comes down to working with the client to understand, hey, which one of these is more important to you, or at what level can we arrive? What sensitivities can we run to say, we can save you this much in dollar value and this much in greenhouse gases, or we can go to the other extreme and then essentially align on some point somewhere in the middle using that function that Ryan just described.
Fantastic. Well, I know that we have other questions that keep coming in, so we do appreciate the audience's active participation in today's webinar. And as a reminder, the team from Enel is going to be sending a copy of the presentation once the event is on demand. So thank you for that. I know that this will be a valuable resource for everybody attending and those watching it on demand. Feel free to come back, continue to watch the event once it has been archived by Zoom. And as always, thank you, Enel, for a fantastic presentation. It's always a pleasure to work with the team. We have a very long-standing relationship with you guys. So again, thank you for providing expertise today. And for all of those who are still on with us, thank you in advance for filling out the survey. So at this point, I'm going to conclude today's webinar. And Liam and Ryan, thank you again.
Thank you all. Have a great day.
Thanks.